Hi, everyone, and welcome to this week's edition of Water Talks with Innovyze. Before we get started, we'd just like to remind you guys that the goal is to create a community where you can come and ask all your questions. Even though it can seem like a webinar, we like to make it feel a little bit less like that by having you guys throw questions at us. So just feel free to throw them in the questions panel and we'll answer them as they come up or at an appropriate time. Also like to point out that we have some really exciting upcoming water talks. Next week, we have one exploring the updates and features and functionalities within InfoWater Pro with two names you probably recognize from previous water talks, Tim Medeiros and Nathan Gertz. And then also like to point out that tomorrow, this Wednesday, we have a webinar on Info 360 Asset where we're going to try and improve decisions and increase ROI on your inspection programs, and you can go to our website to register for that website and go to our Water Talks website to register for upcoming Water Talks. And then also like to point out, we have them through the rest of the month, and then we are going to be off September 7th for Labor Day. Hopefully you guys are enjoying some time away from work and can get some outside time in. Next slide.
Okay, can you hear me?
Yes, I can hear you now.
Okay, perfect. Yeah, sorry.
No
Got
worries.
like a bad network connection there for a little bit.
Can you go to the next slide? Okay, perfect. And your host for today, I'm Hunter Sparks. I'm a solutions engineer here with Innovyze, working mainly with our SaaS platforms. And I've been selling SaaS software in the civil engineering realm for about 2 years. And before that, I have 7+ years of civil engineering industry experience. And we're also really pleased to be joined today by Javier Cantu. He's one of our solution architects with 10+ years of water and wastewater planning, design, and operations experience. And he's going to be your main presenter today. So Javier, I'm going to go ahead and pass it to you.
Thanks, Hunter. Hopefully I don't lose audio here again in a little bit. But thanks a lot for coming, everybody. Really happy to be here. I'm going to talk today about OPM, or Operations Performance Management, which is kind of an approach, and it's a platform kind of approach towards solving some issues. Specifically, we're going to talk about leak detection and energy conservation, within distribution networks. So as many of you may be aware, for the last several years now, we've been working to integrate a multitude of our capabilities into our new cloud platform, which is Info 360, right? Right now, I kind of want to talk about some of the lessons that we learned through that process and how some of these new technologies that we have and are available to the market now have changed the way we solve, our leakage, water loss, and energy conservation problems, and what does and how we're using this tech now to solve some of these problems in a top-down approach. Having to speak about how everything is somewhat correlated or related or anything of the sort, you can imagine the types of personas that we've talked to in the process. There's, for those of us that have experience with software implementation, which I'm sure there's plenty within this call, we know that starting discussions when it comes to water distribution involves many, many, many steps. Take a look at all these stakeholders here, and I'm going to click through because I did not realize that this was on a click. But these are kind of all the different stakeholders that we've worked with in the past to kind of inform our solutions and where we are. Given how many personas, it's hard to imagine one person really being able to do all this work. So, which is why we have teams of people that's helped develop some of these solutions. But it's kind of very important that everybody is consulted throughout that process, because take, for instance, this traditional network that we have down here, your pump stations, storage tanks, valves, and your zones. our city managers may know we need water, right? But that's not the same as to understanding like what the planners are doing, which is where and when to get it, right? Or engineering what they're doing in their design and construction, and of course operations and maintaining it. You know, it's one thing to know that you need an NSF 61 PVC, and another thing to know that you need a PLC with like 12 IOs going to a SQL database and a TCP connector, right, or something like that, right? And the latter of which has added like another layer of complexity to our implementations for our solutions, because uh, now it's software that requires another level of security, given how it's integrated to a lot of online systems. So I kind of wanted to start with one of our one of our customers over in Australia, actually, and kind of go through how this implementation, quite a few years back, transformed the way we started looking at things and how it led to that Info 360 to get to that OPM approach to solving these issues. This particular customer's key drivers were event detection for leak management, improved identification of leaks and bursts, better customer service around reducing response times and detecting daylight deviations in system pressure. Of course, the solution presented within this was Info 360, which was kind of the original version of what Info 360 was here within Innovyze. It was a pretty sophisticated tech stack, and it helped us solve our customer solution, captured snapshots of data such as billing information, mass balance calculations, power consumption data, and it helped automate to a certain degree that non-revenue water calculation. It did the job well, and it did it pretty well. However, it did shed light on a lot of items that needed and a lot of challenges that needed to be fixed, so that we can further drive down into where some of the issues within a system were located. And I'm going to go through that here. So take, for instance, this traditional approach for calculating non-revenue water, or NRW, right? Long ago, it was a very static approach. It was a pretty enormous effort as well. It involved teams of people collecting, consolidating data sets, uh, accounts payable, bringing together the amount of water that was billed, plant managers giving their production numbers, operators setting out aside their data sets that indicated amount of water for flushing activities maybe used or anything of the sort. And of course, all the different sources such as breaks or maybe a recorded actual theft or something of the sort. This concept was and has remained pretty simple at a macro level. How much water goes into the system and how much water gets billed out in order to determine that deficit in between. What the kind of questions that kind of led to our revised approach is when we started getting more and more calls that was asking tougher questions like, what is the most likely source of that non-revenue water? Can it be located? These answers, the answers to these problems were hard to come by, especially at the intervals at which we were collecting data. Sometimes we had a pretty static model as well, or sometimes we had a very consolidated data source for pressure zone. So naturally, we went. Our first step was to integrate SCADA into these calculations and to try to get some of that live data integrated into these network calculations. So what I'm showing here is this a somewhat shoddy representation of a water network. I did my best trying to put valves and setting aside pressure zones. So we understand that we have a lot of data within these networks from our SCADA system, whether it be our storage levels, our pump station run status, pressures, water quality, wherever we have monitors to make sure we're recording the right residuals. And our bigger systems are split up into what we call, district metered areas, or, sometimes they're one and the same as pressure zones. Other times they're just isolatable areas within a city. DMAs have become pretty much a very important factor in a very important way in order to narrow down and drill down the source of non-revenue water. Very much recommended by consultancies all over the world, and of course, it's one way that I would work back in my consultant days to try to determine, or in a more granular level, what are areas of a city that needed most work. There are a multitude of factors that need to be considered when forming DMAs. And of course, even though it can be like costly upfront, the benefits definitely outweigh the needs. For the people or for the utilities that we found that are like, okay, well, we have a challenge in that we can't necessarily go and implement a kind of a DMA system, we had to come up with new and inventive solutions in order to solve these problems to generating virtual DMAs, utilizing our network solution, or anything of this sort. Of course, within those systems, we had to factor in those factors in forming these virtual DMAs, such as the number of connections within the system, the topography around the system, isolation and interconnectivity, and of course, deviations in slopes and elevation or pressures, as would the name pressure zone would entail. These are very highly evolved concepts, and they're accepted widely. I'm sure I'm preaching to the choir here. The only real con, as I mentioned, is higher initial costs when setting it up, but within the modeling system, what we can start to do is kind of set our models aside for those that are very used to breaking our models apart, just setting, maybe they're too big to send all in one, but overall, we get a lot of great benefits in laying out our models and laying out our systems as district metered areas. This allows us to trace down non-revenue water, and of course, get us an improved quality and consistency of our water supply. So some of the challenges that we found, while we managed to achieve some amazing things with our initial approach on how we were going towards our mass balance equations and our numerical approaches, we learned a lot, right? And some of the challenges that we found is that, we didn't have the ability to really customize the dashboard per personas, right? We needed some power users, people that understood a large quantity amount of the IT side of things, the engineering side of things, and the operations side of things. So you need a power user. So now you have a platform that can only be ran by one person or by a couple people within the organization in order to fully understand. So what have we done? Created much simpler UIs, right? Much simpler, and the ability to customize some of these dashboards specific to a persona, right? Lack of telemetry data, just skipping ahead through some of these things. That was a big system issue where we would connect to a SCADA system and then found, oh, well, you have, we have a monitor or some pressure station, pressure monitor out in our system, but it's out of calibration or it's been out for 10 years and nobody really knew, right? So we started filling in those gaps, utilizing some machine learning. Of course, DMAs not being delimited, right? Maybe DMAs don't exist within the system. Okay, well, how do we deal with this, right? Can we break those models apart virtually and simulate those virtually in order to get a very similar benefit within our approach to calculating non-revenue water? And a couple of other challenges as you see here. So in order to solve some of these challenges, and as our systems and workforces have become more sophisticated, the way that what that's forced us to look at is solving the problem more so, not necessarily backwards, top bottom, as opposed to a bottom up approach where we're looking at the asset level information, or we're looking at these data sources very at a system level below, where we run maybe a model. We traditionally we would be involved in only fit into one or two components of that workflow approach. Maybe that's running the model and calculating just numbers. And then of course, utility come in, they'll determine the area of concern, create CIP, prioritize, improve assets, operate and monitor. Then we started getting involved into forecasting those anomalies based on the asset data, calculating, getting more granular into the approach. And in order to drill down even further, we got into the operations performance management approach, right? Where we go based off performance metrics and establish system performance metrics. If we know that last year we had an X amount of non-revenue water, and we were looking to reduce that by a certain percentage, could we establish that as a performance metrics to determine what is needed to achieve those performance metrics? And if so, can we get there, change our system operations to reduce that non-revenue water, and then take that traditional approach of establishing those risks and identifying those scores. So what we're heading towards right now is being able to get more involved into that workflow where we can generate, overlay these data sets in such a way where a lot of these things can be done in real time and can work off a set goal. So to drive down a little deep, and I'm not sure if we've done this in these water talks in the past or not, but I believe we've gone over the concept here before, but to reiterate a bit about APM, which is the asset performance management based approach, versus OPM. OPM refers to operations performance management approach, which is also a platform type of system. What OPM allows us to do is to do prescriptive simulations to allow a user to determine the actions required to get the most efficient types of operations. This is a system-wide scope approach versus APM, which helps us maintain pipes, pumps, and manage our assets. This system-wide approach really allows us to drill down and find locations, either whether it be locations or find system gaps that need to be filled in order to develop or complete a type of calculation. So a lot of you may be thinking it's kind of a lofty goal and it's a lot of data. Quantum computing is not quite a thing. But we don't really need quantum computers for these kind of things. And our models, our numerical models, kind of really allow us to approach the problem in such a way that we can eliminate a lot of the iterations that would be required otherwise, right? So we can use our numerical approaches, use some of our traditional solutions, aid it with the computing powers available within the cloud, and we can then more easily gather and unify asset information, connect the live data sources or historical performance data, visualize these insights, predict future performance, and so on. So the cloud has really bridged some of our capabilities in being able to solve some of these problems, considering that some of these computing simulations do take a little bit more than your traditional computer can handle. So coming back to our example case and how this further helped us improve our ability to drill down into maybe a specific location within a network, utilizing these systems in this platform, we were able to overlay various other historical data sources, apply these process hydraulic simulations in the cloud to adjust parameters and demand nodes inside and outside very specific pressure zones that may not have been delineated, and from there get an approximation for where there may be a probable burst event, right? This burst event, well, you might be thinking in this particular instance, instead of being able to say, hey, this thing happened in PZ1, hey, we could drill down to the point where, hey, we believe that this amount of water is being lost at this specific area. Maybe it's a zip code, or maybe it's something of the sort based off historical incidents, acid age data, and a whole bunch of other things available within that system. So you may be thinking, well, what about where we are not necessarily collecting real-time data, right? Well, this comes back to somewhat of some of the technology that Innovyze acquired about, I want to say 2.5 years, 3 years now almost ago from our friends Imagine. Maybe you guys have heard me talk about Imagine in the past and how we were using some of that information. Well, Imagine helped us leap from one end of machine learning scale to another, right? Where our numerical models weren't fitting a physical system, we were able to abstract any system into real-time predictive models. Think statistical solutions to numerical problems. And this brings a type of adaptability and scalability in places where we may be missing some data. So when we don't really understand a scenario within our systems, or maybe we never modeled a specific scenario within a system, how can we utilize some of the technology within Imagine to fill in some of those gaps where we know nothing, right? Well, utilizing a lot of historical data, whether it be available in a historian or even in some reports that are manually entered, really Imagine our machine learning tools can help us profile the most likely operating conditions via this technique called multidimensional clustering. Here, similar operation conditions form clusters, right, that represent different operational scenarios. So maybe every color, think of this Irish cluster profile, every color being a different type of demand profile. Maybe that's a different time of the day, different season. Maybe that's a demand profile for a main trunk line being offline. If the history was there, the demand profile can be generated around that, and what that really forms is a multi-dimensional kind of performance curve within that cluster, right? In which we can understand, okay, given all these conditions, this is what can be abstracted at a different at a different node, right? So we can start to infer different areas of our system based off everything else moving around it. And that's that system-wide scope view that we take a look in order to solve some of these problems. In other areas where we lack telemetry, in the same way that we use these clusters to develop system performance scenarios, we use those clusters to form soft sensing strategies. Maybe that's a pressure soft sensing strategy or a water quality parameter for ammonia or chlorine or anything of the sort. These soft sensing strategies allows us to fill in those gaps and determine, okay, well, maybe a sensor is flatlining, or we're limited on sensors in a specific area, or something, or we're getting noisy data somewhere where sensors requiring calibration. Can we go and capture some of the historical data to infer in it and provide at least a level of fidelity to a model by inferring specific numbers, right? When we can create these clusters and infer numbers for areas that may not have them, we can start utilizing some of this data within our traditional numerical approaches, right? And we can use it to come up and develop infrastructure leakage index, on a real-time basis. The cloud allows us to do this, daily, right? To abstract and forecast out pipe like a pipe break. In this case, this is your traditional plot for ILI through time. A pipe break here when you see a huge spike, and of course your seasonal and operational changes when you see those changes come up in different model approaches. This also allows us to come in and start calculate, the amount of water that we anticipate to be lost through a pipe burst, right? We can detect the anomaly, estimate a volume, and apply these totals to our reports. And of course, with this comes our very natural ability to apply or to create system alerts and pressure alarms. Alerts are pretty important. I know we have SCADA systems that have plenty and plenty of alarms, but really what ML has provided us, or machine learning has allowed us to do now, is to provide these early alarms on systems to understand whether an event is coming before something happens. So in regards to managing our energies, in the very similar way that I mentioned, we're creating these clusters for a system. We can use the same data sets to inform our operational activities. We do this utilizing this OPM approach to develop a system performance curve for an entire network or a zone. This is a very simplified version of that system performance curve, and it runs very similarly as you would a pump model or a pump curve, right? Where you have a design point for a system at a specific demand node, and within that curve, we can actually solve given a specific outcome by either indicating a desire to run at an optimal OPEX or cost operating point, or an optimal water quality operating point, with, of course, all the system constraints and permit constraints in mind. As the system demand changes, so does the profile of this curve. It could change daily, it could change every hour, right? And as such, those recommendations on how to run the system change every moment that system profile changes. But generating these multi-dimensional performance curves really allows to move along that line to optimize how our systems are run. And of course, we can then use this curve to solve for compliance, assurance, water quality, and cost performance. So coming back to our customer and how we utilize some of this information to develop these models. Here is a kind of an overview of their system profile, right? They serve over 7 million residents, have 32 DMA zones, and they distribute roughly almost half a billion megaliters per year, a little bit over that. So the system's been pretty much built to generate demand models throughout the entire, all their DMAs, right? Inside those demand models, we also have simulation models. There are pump station simulation models. They're looking at run speeds, discharge pressure, VFDs for wherever that's available. We're generating reservoir volume models to understand on-off areas. What's the spend at different volume levels.
And we can't hear you right now, Hobby. Can you hear me? Yeah, Javi, if you can hear us, we cannot hear your audio right now. I see that you're talking, but we can't hear you. Still can't hear you. All right, so working on fixing some of the audio issues here. Oh,
Is this can you hear me, Hunter?
yes. Yep, we got you back.
Sorry, I had to dial in on my phone.
Hey, that's
But
how they know it's live. They know it's live, with these little audibles. It's not just a canned demo just sitting behind the screen. So I have to keep it exciting.
yeah. So I mean, I don't know if you had an opportunity there while I was figuring out the thing to kind of go through some questions so that I can possibly stop here before I go into how these clustering techniques were used to create these demand models.
So haven't been able to go through them, but I guess one question that seems to come up is when you are coming in afterwards and setting up those virtual DMAs, how is that process and how are you able to do that if the system wasn't set up for it in the beginning?
Well, it's very well. It's through this process of doing these developing clusters for a system and utilizing system dynamics and historical information to come up with, how a system may be operating in a specific area, right? It takes some time to go through this, but more often than not, we can actually assign, typical profiles to be reviewed and looked at by, let's say a piece of code, like a machine learning code, so that they can go in there and start, I guess, finding different, at least defining the boundaries of different model scenarios to develop, that's kind of what you see on the screen now. These simulation models for that have different demand signals across the network, right? And we can use some of that information.
And then it looks like we got another one that just came in. You said you can predict a line break. Have you actually predicted a line break that actually happened?
Yeah. So that's usually done in the same way that we're developing these ILI indexes in the past, right? So in order to get a proper prediction with high probability, you need to have good data in to have good data out. But if there's enough data that to train these models, which we have had it in the past where we've seen, okay, we have all this data available, we can train, we can forecast out what we see based on operating conditions in these cluster demand signals, and we can understand when that's going to happen. Of course, because these models are very dynamic and prolific, usually the the timing is, an hour. We can't really look out 24 hours into the future and find something like that, because normally a pipe break is in the works, or for many, many years before it ever really happens, right? So what you see is the system dynamics change maybe about 15 minutes or an hour. Sometimes we can find it 2 hours. I can't think of a time where we actually were able to predict it, like a whole day ahead of schedule, right? At that point, we would require probably some different types of sensors in order to do something like that.
But that's one thing where, just to piggyback on that, that is one of the things, maybe not predicting it, but being able to get the alerts from the cloud. That is setting up those alerts are important, and you can get those alerts if the incident is happening. And you also have the power within the system to run impacts if you were to have a pipe burst, by looking at, likelihood of failure, maybe an asset, that's been under there longer and you want to do a replacement project. Well, what happens if this pipe were to burst and run for an amount of time? With this cloud technology, you're able to look at some of those impacts and really start getting some of those, real-time alerts sent to your phone, which I think that's where the cloud is really taking it to the next level.
Yeah, for sure. I would say Imagine does one of the best jobs there at being able to look into the future. And all that Info360 Insight product line does a very good job at simulating those impacts and seeing how that system needs to change in order to still meet its demands, right?
Yeah. It's really cool being able to see them, work together, having the machine learning side and having the impact side. It's been really exciting to have both kind of on the same sideline, on the same team.
Yeah, for sure. So kind of like a brief example, I'm just going to go to the next one on kind of what that view looks like, at least on the Imagine side. And to make it clear, the Info360 and Imagine are all using the same data sources. It is very possible that on one end, Imagine may have a different integration that Info360 may not have. But more often than not, working off the exact same database, same consolidated data sources. This allows the system to feed back to one another information. In this particular instance, given the very specific outcome-based approach, that OPM-based approach, you can ask the system to generate different schedules, pump performance schedules, to always be solving for where those pumps need to be ran to have that optimal cost approach, which is the goal set up here. In black, what you show here is the actual settings of some pumps and their VFD frequencies and where they should be. These are the actuals. Or blue line is the day and time the snapshot is taken, and orange line is the predicted future operation scenario based off all these cluster demand clusters that were generated by the system. So pretty useful for some operators in regards to being able to understand, oh, okay, well, I need my staff to be more concerned or more in our area about low lift pump station 1, where you see some dynamics versus 2, where it's saying, okay, well, this is going to be off generally for the next several hours. So as demonstrated in this figure, we can observe significant amount of energy savings that are achieved during the summer scenarios for the pump stations listed here. Well, we have pump stations 12, 27, 20, and 30 and 40, which were working in conjunction. So on the top side, what is shown is a historical operation scenario for a specific DMA, which is a district meter area, where pumps were running as it's, and on the bottom is the simulated scenario where pressures were maintained, quality was maintained, but those pumps were operated to optimize around existing storage capacity in energy rate tariff schedules. So there are a lot of instances where some utilities have maybe a tariff schedule for the day where they're paying peak or per kilowatt hour during the day and pay a lot less at night. Well, applying some of these schedules generated by the models, we can see already in the summer a lot wider representations of those costs, with the darker red being some of the most expensive days on record for the specific DMA, and the lighters being a lot lower cost associated with those specific demand profiles and times. So of course your 3 seasons, very naturally, summer demand going up, a lot more expensive, and then a little lower on the winter. Couple of results from that specific study. Once we ran and simulated these models, in one DMA alone, right, we were able to achieve, $52,000 in savings. That's a 20% reduction here that we found in operating cost alone, and that's not taking into account any of the man hours saved associated with understanding where people needed to be when and where in time, instead of having to do a time-based kind of operation throughout a city's pump stations. Any questions here? I know I wanted to stop kind of here early and see if we got any more questions in regards to this OPM approach that we're kind of taking now. Hunter, is there anything else coming in on your end?
The only question that I see that has also come in is when we were talking about the cloud. It says when you use the term the cloud, are you essentially saying computing power? What about the cloud solution is better than saying an on-prem solution?
Oh man, that's definitely do you want to take a stab or do you want me to do it? I'd be more than happy.
Yeah, I mean, I can start kind of doing a little bit of the explaining on it, and then you can piggyback on the back end if you want.
Yeah.
So with the cloud, it's the computing power, but also the storage that we're dealing with, where it lives, and the cloud, it makes it more scalable. So as customers need to add capacity and get bigger, it's much easier to do that. You get, more real-time updates. The accessibility, you can have more mobile or remote operations that can tap into the cloud. And as you're able to grow, it really can grow with you because it's scalable and it's elastic, and it's really easier to integrate across different business areas. Are some of the main ones that come to mind. Javi, do you want to add some on top of that?
Yeah. So at least when I talk about computing power, I think about the traditional machines that you're using to run, let's say, InfoWater Pro. If I have any InfoWater Pro power users on this call, they understand that they probably have one of the best machines at their utility or at their company, right? They are carrying, maybe 32 gigs of RAM, a GPU, a dedicated GPU, and probably top of the line processors on their computer. These are, I don't know, I want to say maybe sometimes $4,000 computers. Sure, they might be getting a little bit cheaper lately, but they are still pretty expensive PCs, and they are still taking a while to compute some of or run some of our simulations. The cloud and saying computing power of the cloud allows you to run those specs on any machine, and not just those specs, but maybe even better specs. You can dedicate 64 gigs of RAM. You could dedicate an even better processor to it. You could dedicate better GPU power to it. And that's essentially what's being done here. Depending on the size of the simulation, that simulation gets its own particular set of specs required to solve that problem.
in order for it to happen quickly, as opposed to us having to, go and find one person in our organization that has the best machine. This is a huge benefit because we're no longer paying, at least as an organization, for these very expensive machines, maintaining them and keeping them up to date. Their maintenance on them can be pretty hefty, and every couple of years, technology improves. Utilizing the cloud allows us to take advantage of the latest to the late computing power at no extra charge, at no maintenance cost either, and allows any user that has a Chromebook, for the most part, to perform a majority of these types of techniques inside of them. Okay. I hope that example kind of at least shed some light on why the cloud is kind of a big deal to us. Yeah, I know one of the things when I was helping in support for a while, one of the things that I would mostly hear troubles about is, hey, my product isn't working, I've been trying to run this and my system keeps crashing, right? And it's usually a user on XP or something like that, using a small computer trying to generate a very, very large simulation on their PC. So I had to explain, okay, well, we need to find you another machine, talk to your organization, and so on.
Yeah, and
So
especially, what we ran into with what we've been into with the last year and a half, some people having to work from home, they're not really being able to pick up those heavy machines and bring them home with them to run these simulations. So, being able to be more mobile with that solution is, a benefit that we could have seen really in the past year and a half.
Correct. And I have a pretty good question here. For clients that are InfoWater Pro users and invested heavily in other software such as Pi, can you integrate pretty much the AI and ML tools into Pi without purchasing Info360? So Info360 in itself is it's a platform, but that platform is going to have different features and solutions built into that. A short answer is right now you cannot. Eventually, what we would like to be doing and what we'll be doing is utilizing APIs to integrate a lot of these systems. We aren't really looking to replace something like OSI-Pi. OSI-Pi is an extremely robust tool that allows you to record data down to like the second, sometimes every 15 seconds. To process that much data that quickly is still not quite into our capabilities, not just as a company, but our physical computing capabilities. At least until we can figure out quantum computing. This isn't a replacement for OSI-Pi. You should be able to use APIs in the future. And Info360 is still going to be differentiated from systems like OSI-Pi by providing the tools that InfoWater provides, right? InfoWater Pro or anything of that sort. So as of right now, there are lower tiers available of Info360 that do specific things, and we'd be happy to review the kind of problems that you're looking to solve, Anthony, to see what mixture of solutions best fits your needs. Yeah.
And I think you did a good job, really good job explaining that, because it really points to the fact that Info360 being the platform, and it can really be tailored to what you're trying to do. It can be as specific. The goal is for it to be as specific or really as robust as you need it to be.
Yeah. For those that use OSI-Pi, I would say that is our the number one system that we use to integrate with normally, right? It's an extremely robust, very capable tool. Allows us to sometimes work hand in hand with our customers to even do closed loop systems where we can actually push recommendations back into a system. You know, it all just depends on the kind of network infrastructure available within our customers. Well, I hate to use the word mainframe because it's overused in sci-fi, but yeah, mainframe. Sure.
This is a real world application of it. It actually does
Yeah.
happen. It is used in the real world too, not just the sci-fi movies.
Yeah. I know my girlfriend gets on my case sometimes. She's like, man, so many words. Are we watching a sci-fi channel? Like,
It's what we deal with every day. You know, there's a part of, you know, sci-fi being science. So I guess this is just proof.
yeah, well, a lot of it informs us. And well, really, not just informs us, but also inspires us, right? And helps us understand kind of where we want to go with some of these things. I guess just we're here close to the edge of the hour. I'm not seeing much more questions coming in, but to kind of end on a somewhat happy note, because I don't want anyone to think that I'm trying to say like APM is not right or it's not beneficial. APM is extremely useful, and you'll see a lot of conversation come from us at Innovyze about the APM approach and how we're even making our asset software a lot more robust, utilizing this asset performance management approach, right? Some systems like our Info360 asset platform that is out now. And if you guys have any questions, I believe we're going to be talking about that next week or
Tomorrow.
Tomorrow. That uses an APM approach. Really, the best systems ultimately will have a strong asset management program coupled with a strong operations performance management program working together. They can inform each other, give each other data sets and exchange different results so that you can determine if a specific asset is drifting from its operating point and how it's affecting an overall system solution and scope. Yeah, I'd be happy to talk more to you guys about it. And if there are any questions, definitely feel free to reach out to either Hunter or myself. And of course, the traditional John Crochet, who is now taking care of, I think, the Western region, but we also have Nathan Gertz and Timothy Madreas. I think that all of you have heard speak at this point. We're all here to answer questions, and we'd be happy to share more information on how to use some of these tools. And I'll stick around here just for a little while and sip some coffee in case there are any more questions that do come in.
And just another thing, just to piggyback on that, since you were bringing up the Info360 asset, we do have, we are still open, I believe, for signups for the beta program for Info360 asset. So that's going to be a really exciting tool.
And I would say if you guys can convince all of your organizations on that beta program, it's a wonderful opportunity to at least get started on some of those ingestion services, data ingestion services, very easily with our systems, Info360.
Just monitoring the questions just to make sure didn't miss any, but I think we got all the ones that are coming in.